Hello and welcome to the Data Engineering Podcast, the show about modern data management. Have you ever woken up to a crisis because a number on a dashboard is broken and no one knows why, or sent out frustrating Slack messages trying to find the right dataset, or tried to understand what a column name means? Our friends at Atlan started out as a data team themselves and faced all this collaboration chaos. They started building Atlan as an internal tool for themselves. Atlan is a collaborative workspace for data-driven teams, like GitHub for engineering or Figma for design teams. By acting as a virtual hub for data assets ranging from tables and dashboards to SQL snippets and code, Atlan enables teams to create a single source of truth for all of their data assets, and collaborate across the modern data stack through deep integrations with tools like Snowflake, Slack, Looker, and more. Go to dataengineeringpodcast.com/Atlan today, that's ATLAN, and sign up for a free trial. If you're a Data Engineering Podcast listener, you get credits worth $3,000 on an annual subscription. When you're ready to build your next pipeline and want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With their managed Kubernetes platform, it's now even easier to deploy and scale your workflows, or try out the latest Helm charts from tools like Pulsar, Pachyderm, and Dagster. With simple pricing, fast networking, object storage, and worldwide data centers, you've got everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode today, that's LINODE, and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Your host is Tobias Macy, and today I'm interviewing Mário Pereira about building a data management system for globally distributed IoT sensors at Vopak. So, Mário, can you start by introducing yourself?
Hi. First, thank you for having me. So, my name is Mário. I'm from Portugal, but I'm currently living in the Netherlands. I work as a senior engineer at Vopak.
And do you remember how you first got started working in data?
So, first I started in tech startups. I worked at OutSystems. It's a local platform. And I worked then at MessageBird. It's the Twilio competition. And I worked in majority in the data cloud infrastructure part. And now I started working in the edge data infrastructure. So for around 10 years that I'm already doing it, but majority using cloud technology.
So the company that you're at now is Vopak, and I'm wondering if you can just describe a bit about what that business is and the types of information that you rely on to be able to power the business.
So Vopak is the leading independent liquid storage company. It's a Dutch company, the oldest Dutch company. It's 407 years old. The business, what they do, Vopak stores vital products. So everything that is vital for mankind. So it could be oil and gas, industrial chemicals. Currently, Vopak has 73 locations. When I say locations, it's plants, facilities, terminals, which stores the oil and gas in 23 countries. What the information that's the business or powers the business is the status of the liquid inside of the tanks, the flow meters, the state of the pump, the truck, the information that are inside of the truck. So all this information that is on site empowers the operational part of the business, the supply chain of the business, and the operability of the business itself, the facility itself. So what we do at Vopak, and I will explain later on, is how we ingest this data and transform this data at the edge that empowers the business.
And you mentioned that you've got a few different categories of locations and different types of information that you're collecting. I'm wondering if you can talk through the different types of sensors and edge devices that you're relying on and what types of consistency you might have within a particular category of location and the degree of variance that you're dealing with across your overall fleet of sensors and the sort of matrix of complexity that you're dealing with.
So we have 73 locations. Currently in production live, we are in almost 18 right now. And every location is different, totally different, with different sensors, different edge devices. What happens is, so currently what we do at the edge, we ingest the data. So from flow meters, sensors, so industrial sensors, not your normal sensor. We flow meters, so we know how is the speed of the liquid that is go, the temperature, the level of the tank, weigh bridges, so we can weigh the trunks. We can ingest the data from license plates, readers. this is funny, from drones. We have drones that inspect the tanks. We have robots that inspect the tanks. Camera, in this case, image camera. Everything that has a data point, so everything that has a sensor, we grab it, we ingest it. And then this data is then sent to its processes at the edge before sending to the cloud, regardless the variance. What happens is that, for example, we have a tank. We are pumping the liquid to inside of the tank. You don't want to send all data to the cloud. So you get still, maybe you only want when it starts, at the middle, and then at the end, or you need to let it flat, get stable, right? In this case, we use what they call deadband, and in some other sensors, we use what they call sinking door compression algorithm. What happens is that this algorithm cuts values to some degree that are in the middle and which you don't need. So what happens is, for example, we are pumping and the value is constantly changing. We only get some part of this value, the value that really changes, for example, because it can go to a value of 6 digits and you don't want all this big value, and then we cut it. This is all done at the edge. What we do at the edge too, on the data, we do some, I will not talk like this, but it's a complex event processing. So based on some data change, we trigger another change. So for example, if a truck arrives to Weybridget, automatically we get the license plate and automatically we get the weight of the truck. And then based on the billing, we are able to open or not the door to the truck to come in. So there is a lot of things that we still do at the edge before sending to the cloud.
As far as the selection of sensors and the deployment of sensors, I'm wondering how much control or oversight you have as the person who's responsible for dealing with the data that they're collecting versus just having to deal with accepting whatever the terminal manager happens to decide is the most economical or, best option for them to be able to install and maintain in their physical locations.
In this case, it really depends which sensor it is and which supplier it is and which type of terminals. For example, this is public. Recently we invested in a company that provides sensors, industrial sensors, and the reason is because the industrial field and in our field, a lot of the sensors needs to have specific certifications. For example, ATEX certification, because it are places which hazardous conditions. What majority of the times as an edge team, what we ask, or we have something in the saying, is that we would like to have a sensor that connects to a DCS, and then from the DCS, we would like to have the data from that sensor. DCS, it's a common word from industrial world. It's a distributed computer system. We kind of have, sometimes we are able to say, hey, if it's a new terminal, bear in mind that changing these sensors is not something that you change every day, okay? You are not going to build terminals every month. We are talking about facilities with 30, 40 years. And so when you build it to last. You build like, some of our terminals have like 100 years, Of course, you constantly upgrade your sensors and your terminals, but it's not something that, you upgrade every day or you change every day. Regarding that of the selection of the sensors, it's what we do in this case.
And then as far as the general capacity for computation and storage, both within the sensors and at the edge locations where those sensors are operating, I'm wondering if you can talk, at least in terms of orders of magnitude, what kind of compute and storage and processing capacity you have to be able to push more of your logic to that edge location so that it doesn't all have to be centralized.
Currently, in a general, we are currently processing 65 million events per day at the edge. And in the cloud, we are storing around 8 billion events. So the computing of this, I can already tell, but we are using IoT Greengrass from Amazon. And IoT Greengrass from Amazon allows us to run Lambdas, which you run in the cloud, on-prem, inside of your Raspberry Pi. So the computing power of this, you don't need a really big machine, okay? You can run this in a Raspberry Pi. So from a computing power, it's a very low spec computer that we have there. Currently, we run it in the physical server and in the rack, and that's because of compliance. Once again, because of the attack certification, I cannot just put a server or a Raspberry Pi inside of a tank or near a tank because it can explode. So it's a very low spec computer which processes all that information. And then this is because we use AWS Lambda at the edge. So on site in this case, because we use AWS IoT Greengrass.
As far as the processing that you're doing at the edge with that Greengrass service, what are some of the types of filtering and pre-processing and logic that you are pushing out to that edge location in order to determine what events and what aggregate data you actually want to centralize?
To give more information to that question, we use, in order to aggregate and to ingest the data first, we use OPC UA. OPC UA, it's a machine-to-machine industrial protocol. So what we do, we connect to a OPC UA server, we have a client, and we ingest this data. The data that comes, it's very hard to understand from IT, software engineer, BI, data science perspective. It is like example temperature from a tank originally. So as a raw data, it comes like CV 337.CV and then 37. So what we do at the edge, besides the filter of the deadband, as I told before, we add context information. For example, and this depends of the terminal, by the way, which type of sensor it is, which type of measurement it is, which type of unit of measurement it is. So we have much more information. And then we have some business-related information, like the location, the specific location of the sensor, timestamps. So we have the server timestamp, we have the sensor timestamp, we have the ingestion timestamp, transformation timestamp. We are able to, at the edge, besides filtering, we are adding information, so transforming the information at the edge. So what happens, so giving already a little bit of the architecture, we have IT Greengrass, and then we have 3 lambdas. Okay, so one lambda runs PCOA client, which ingests the data. So this data, very raw data that is very hard to understand. Depends on the terminal, but can come on change. So every time there is a new value, we get it, and can on quest on batch. For example, we can call the OPCOA server every 1 minute or every 1 second, and see if the value changes or not. So then we have a lambda that transforms the data, that gives the context, which type of sensor it is, in which location, which unit of measurement is using, the method that is using to measure. Okay, because in a tank, it's like a cup of glass, right? It could be half full or half empty, and these can change on the tank. The sensor could be measuring if the tank is half full or half empty. And then we add this information, as I was telling, we transform this information, and then we have a lambda that stores the data locally, and we have then the normalization lambda, or transformation lambda is how we call it. It sends the data to the cloud, We store it in MongoDB, but going a little bit back, we have AWS Kinesis that streams the data to an S3 bucket for the BI and data science team. And we have AWS Batch, which batch the data every day to other departments to use the data. So the complexity of the things, the transformation, as it asked, it's done at the edge and filtered at the edge using the normalization lambda. The ingest ingests everything, normalization transforms, and then we have the one that stores locally in case we need, example, if the internet fails, we are able to cache, by the way, I didn't told, but we are able to cache the information for around 1 hour. But if the internet fails for a longer period, we may need to go to the data storage, the local data storage. So this data is then, as I told you, sent to the cloud through the normalization regarding your transformation and filtering.
To the point of the network failures and the potential for not being able to receive data in the central location for, up to an hour or more, I'm wondering what the tolerance is for those types of latencies and some of the ways that you're able to mitigate issues due to that lack of central coordination by pushing more of the logic to the edge for any types of decision making that has to happen in a more real-time fashion.
So as I told you, we can cache for 1 hour. We try as a team to make it the maximum is 50 minutes of data. We shouldn't lose more than 50 minutes of data. Okay, so we cache 1 hour of data. If you say, okay, if everything goes down on a location, then even the industrial system goes down. And that's very hard because these industrial systems are made to keep running forever. Okay, so they are very redundant, and our system is very redundant too. We have two ingresses. In case of one fails, we can use the other one. Even if it fails, there are safety mechanisms. We currently only ingest. We don't write down, so we don't give instructions yet to the sensors, okay? One day maybe we give instructions to the sensors, but we only ingest. So if there is a failure, everything fails on site, not only us. So what I'm trying to say is it's very hard to have something that really fails. The internet, we have double connection to the internet. So yeah, we built something. When we built it, thinking about scalability and highability.
In terms of the retention periods that you have, I'm curious what the utility is of this sensor data as you move beyond the time horizons of maybe an hour or a day and into weeks and months and years, and what types of longitudinal analysis you are looking to be able to do over those longer time periods versus just saying, this particular category of sensor data is useless to me past 5 minutes.
So at the edge, we store for 2 months. And the main reason is because if we lose data or something, we are able to fetch it again. Or if a local application wants to access it in case of emergency, it's there. In the cloud, as I told you, I can say it goes to MongoDB, okay? And then we have an API on top of it. Majority of this data, it goes, I didn't told, but Vopak is going through a massive digital transformation. And the reason that Edge was built, this product was built, is because during the digital transformation, we found out that we store more than oil and gas and other liquids. We store vital data too. Okay, so that is very important for us and for customers and partners. So the API provides data like reporting the end of the day or give me the current value right now. And this data majority of the times is called by our P systems, CRM systems, even our customers. This is one of the good values, is currently they're able to see the state of their tanks. We have a mobile app, tablet app, where the customer can see the data, not only the people on site, the operations, but the customers too. So they can see the status, what is happening on the terminal. And then longer data, we store it because we have a data science team, okay, and machine learning team besides BI team. So what happens is we store it in the bucket, and of course in the bucket then we have lifecycle, okay, and this lifecycle it's coordinated with the data science team. So when they train their data model, so currently they do predictive maintenance, for example, we do analytics over alarms and events. So alarms and events, it's a type of communication protocol that exists in the industrial field or domain. For example, if you are having leaks, it triggers a data point, an example. Or a pump is too busy, triggers a data point. And then we do analytics over this. We have our data science does asset performance optimization in order to understand why it doesn't work so well. We do loading and offloading optimizations. We have these jetties and these arms where it's used to pump the liquid, and then we do optimizations on it. And this data, of course, needs to be stored for many years. When you train your data model, you need a lot of data and good data to train them. For example, predictive maintenance, you need to, for example, vibration. It's one of the things that I think everyone uses is vibration in the spectrum. It's easier to detect. With that, you need a lot of data. So currently, we are storing all data in S3 bucket for that. But bear in mind that we built this in 2018. So we are starting building in 2018. So we are starting Science 2018. Even that, probably to have more confidence on our data models, we're going to need even more data from more terminals, from more ears.
You mentioned that this overall effort of building this full end-to-end IoT platform is a fairly recent exercise, and I'm curious, you mentioned that some of these terminals have been in operation for on the order of 100 years, and I'm sure that maybe not for the full 100 years, but at least on the order of decades, they've had some sort of electronic sensors and they've been doing something with that. And I'm wondering what the existing situation looked like before you started this project and what some of the evaluation and planning looked like as you were deciding what is an optimal architecture given the existing physical investments that we have and the constraints that we have as far as access and power supply and reliability, at these various locations, and just what that evaluation and planning looked like for the technical selection and architecture design, and how you have been thinking about being able to reverse engineer this end-to-end system on top of physical limitations that have been in existence since before you became involved.
What happened here is that the industrial IoT, not only IoT, but more precisely on the industrial IoT, the field is very segmented. Okay, you have a lot of companies that are building industrial IoT platforms, ABB, Emerson, Yokogawa, Honeywell. What happens here is it's so fragmented currently. So we have one company that is very good at ingesting. You have another company that is very good at transforming at the edge, but is not so good at ingesting. You have another company that is very good at doing the predictive maintenance. For example, you have Foghorn that is very good at the edge, doing machine learning at the edge, or AI at the edge. During the selection period, so we went through multiple suppliers and providers that were already being used on the terminal, and we give it like a problem. We have this problem, and we want to solve it. It's like a MVP lookalike. We give it to AWS, AWS partners in this case, all these companies, Ignition, for example, PTC from Kepware, Siemens. We give it this problem and say, hey, show us how can we solve this. Do a demo, a prototype. And then they all come up with it, and then we did an evaluation. Which one it fits our enterprise architecture, which one fits the current acknowledgement and application and landscape we already in-house. So there was this process of selection, okay? We didn't just jump to one. It took like 6 months to have the selection phase, to proof of concept, to test on the field. And we didn't do a big test. Huh? We tested very small, like with one sensor or two. And then we saw, okay, how can this scale? I didn't tell here, but we have a very small team. I was lucky to hire at this time, which is very hard to hire good people. I hired 3 very good engineers and seniors that helped me build this platform. So we thought, okay, we have a very small team. We did the design, the solution design, what we wanted, and then we went through all the suppliers to see which one was better for us at the time. But bear in mind, we are already building, we are 18, but we are constantly still looking for other platforms. We never stop evaluating, because you could have that, for example, for the people that are listening to this, we built our product, right? But for example, Amazon now has IoT site-wise edge, which is in the end the same as what we built, which is funny because we built providing all the time feedback to Amazon. Hey, we are building this, giving this, maybe you want this, and they now recently did the same. But it's not only Amazon. Google, I think, have something similar. Microsoft has something similar in Azure. And we are still checking maybe what happens if we go to site-wise edge. What we need to upgrade, what we need to change. Yeah, so that was a little bit of our process and continuous process, We constantly still building the platform. We didn't build and, okay, it's done. No, we are doing step by step still.
So now your modern data stack is set up. How is everyone going to find the data they need and understand it? Select Star is a data discovery platform that automatically analyzes and documents your data. For every table in Select Star, you can find out where the data originated, which dashboards are built on top of it, who's using it in the company and how they're using it, all the way down to the SQL queries. Best of all, it's simple to set up and easy for both engineering and operations teams to use. With Select Star's data catalog, a single source of truth for your data is built in minutes, even across thousands of datasets. Try it out for free and double the length of your free trial at dataengineeringpodcast.com/selectstar. You'll also get a swag package when you continue on a paid plan. Given the fact that you are still in this phase of proving out the solution and scaling it up, I'm wondering what the criteria for success are and when you can determine that, yes, this is exactly what we're looking for. We're just going to continue investing in this structure and strategy, and we're just going to scale it out across our entire infrastructure, or to the contrary, saying, okay, this isn't quite meeting our expectations. We actually need to stop and rethink and maybe tweak the formula a little bit before we try to hit that full scale company-wide adoption.
Product itself was a success, because as a company, we were not able to see this data, to get this data. It was in silos. Our team is even like a use case inside of the company, because the company is not that company. We wrote the code, we built the code, we automated the deployment. It's quite funny when I say, okay, we are non-tech house and we do microservices, lambdas, and we have a code coverage of 99.5, and we have unit tests, regression tests, smoke tests, load tests, static code analysis, everything inside of CI/CD, and everything is automated. It's quite funny when we say we did that. So the product in monitoring and logging and tracing, when I say the product itself, it's a success, and we are already scaling it. But, probably I mentioned before, we are always looking to see if there is something even better. We're not just going to stop. And this product is already giving a lot of insights and information to other departments. It's quite nice to see that now we are doing digital twins, which we create the model of our terminal in 3D, and people can see in real time the liquid flowing and the temperature, and it's quite nice besides the other initiatives, but it's something that you can see yourself. Or being on the terminal and you see people using smart glasses and they are able to see in real time with the smart glasses the data of the assets of the tanks through the glasses, because they are getting the information from us. So it's a lot of things that you already say, okay, it was a success. We are already scaling it. Of course, as you said, okay, tweaking. Of course, that sometimes time we need to see, let's say, we start noticing that there is a limit in greengrass. Every technology has a limit. So when we start saying, okay, we need to filter even more the data, or maybe we need to deploy multiple green grasses in a location, of course, there is always, as I told you, a tweaking.
In terms of those scaling issues, as you are starting to bring more terminals online and starting to maybe experience a greater degree of heterogeneity across the different sensors and the availability of data, I'm wondering how you have been addressing that and some of the complexities that you're dealing with as you continue to expand on the usage of this architecture that you've designed.
One of the challenges, this is about the challenge, is the contextualization at our scale. Okay, the sensor itself, grabbing the sensor itself, the information, it's easy because of the UPC way is very standardized, and all suppliers have it, and the configuration of it, it's majority standardized already. It's the contextualization, because every terminal is different, but it's not a technology, but a process mindset that you need to change majority of the times, and communication. The challenges is contextualization of the data, so you know that is really a flow meter type, and that is the type of measurement which that information is correct. Okay, so the data quality of it, let's say, the trustiness of the data. That when scaling, it's the biggest problem on this case, because you need to communicate very well with the people on site, with engineers, and you need to explain, hey, I need this information from this information. So you need to adapt very easily to the people that you talk to. And not only that, but the expectations, When scaling, I think the biggest challenge is mindsets, people knowing of this data and this type of data with this context to do this and this and this. The adoption and the data quality and the context, I think, not on the technical part. Because the technical part itself, if you built, in our case, once again, I was very lucky. We built with the mindset from automation from the beginning. So the more terminals we onboard, it's the work itself, it's the same. It's more we grab the data and transforming the data with the correct information. So with giving the correct context at the edge.
As far as the quality aspect of the data, I imagine that that's quite challenging, and understanding what is the lowest common denominator of information that I can expect across all of these different sensors, and then being able to also take advantage of the variance where maybe one sensor, say it's a flow meter, it measures in terms of liters per second, and then another one is gallons per minute, and just being able to make sure that units are correct and that you're able to aggregate the information and try to maintain fidelity and not just kind of bring everything to the coarsest level.
That's the biggest challenge right now, is that currently our automation system, in this case, I know it sounds very strange, but the terminal on site gives us a file with all the context information. We have a CI/CD then pipeline that transforms the file, and then it sends automatically downstream to the CI/CD pipeline, sends automatically down to the edge part. And then we have some validation rules that validates the file of the engineer that gives to us on site. So we have some kind of control on the validation of that data. What happens is if the data is wrong, so the data migration, right? The data migration, the fix that, if it's in the cloud, as I told you, we are storing 8 billion records. Doing the change, it's then a little bit more problematic, because of the scale of the amount of data. It takes a little bit more time to change it. Yeah, I think when you work on this scale, people are already used to it. So, yeah.
And then another interesting challenge of dealing with IoT data and maybe juxtaposing that against what a lot of people who are working in sort of standard corporate data ecosystems are thinking about as far as things like lineage. I'm wondering how that translates for an IoT perspective, where you say, this data point or this aggregate set of data points is coming from this category of sensors in this physical location. This is the trip that it took from the edge location to our central storage. These are the transformations that were applied on it, and just managing data lineage and sort of data cataloging at that scale where you're dealing with thousands or hundreds of thousands of sensors in dozens of different physical locations, and some innumerate number of pipelines that are going to be processing the data for different machine learning or analytical use cases.
The data governance itself, it's quite funny because I was listening on this podcast any other day regarding Monte Carlo and monitoring, the data quality monitoring. We kind of built our own Monte Carlo where we built SLOs and SLIs over the governance and the time. For example, the processing time, okay? So currently, from the sensor to the cloud, it takes half a second. So ingesting, processing, and storing. Our monitoring system monitors that time. We try to go from 1 minute. Max is 1 minute. If it's higher than that, then someone will wake up. The 50 minutes, as I told you, the data quality we monitor let's say if we have a flow meter and suddenly the flow meter is measuring kilos and we get like 2 billion records with that, let's say not 2 billions, but 100,000 records with that, we have monitors that triggers an incident. Luckily, once again, our system is very robust. In 3 years, I was only waked up at night. In 4 years, 3 times. We don't have a lot of incidents until now. Let's see what happens when we are live in 72 terminals. But for now, in the 18, we didn't have any problems yet. We are building the strategy, the data governance monitoring for it in order to prepare us for the future. Yeah, it's a little bit a leap of faith and see what we're going to be getting next.
And then going back to what you were saying as far as some of the business users looking at real-time aggregate flow information, from a central terminal, or terminal managers walking around with smart glasses to be able to see, these are some of the predictive maintenance things that I need to be considering. What are some of the types of new capabilities and business processes that are enabled by being able to actually collect and aggregate all of this information in near real time, and some of the new kind of business use cases that are yet to be considered?
As I told you, the customer now is able to access in real time information of the tanks. We can even provide to our partners and suppliers, okay? Because Vopak is something like a man in the middle in the distribution of liquids. We store and then we give it to someone else sometimes. So from a business, now the customer and partners can see that information. From operational perspective, as I told you, now the terminal manager can use the smart glasses, autonomous robots like Boston Dynamics for asset inspection. So we don't need to send people inside to see what is happening. Because if there is a problem in the tank or flow meter or the pump, the operations will stop. It means that then the customer doesn't get the liquid. And because it's a vital product, it can happen. It never happened, but it can happen. It can happen that we stop a country because, for example, if we look at when Colonial Pipeline was hacked, for example, in the United States, like half of the country stopped. So all these things, when we stop, we need to avoid as much as possible to stop. So our data, it's one of the key pillars of the digital transformation of Vopak. So with this data, then you create all these initiatives that help the customer and the company.
Continuing on this discussion of the types of impact that a failure in the physical plant can have and some of the interaction with the sensor data, I'm wondering what are some of the other types of ramifications that might happen due to failures in the data collection and analysis, or the physical failures that can be reflected or have an impact on the sensor data that you're processing?
As I told you, we only read right now. So the systems we don't write down. So if there is a failure, not because of us, so we just ingest. In the case of failure, we don't get any data. Of course, then the person on site clicks on the app and doesn't get the actual information. But however, they are still on site, So they have this control system, like power plant, imagine, lookalike. They have this control system, and 100% sure they will have an alert on their industrial system, or they already have someone looking at it. Because if there is a problem on the sensor, or we don't get the data, or the OPC-UA, that's why we use the OPC-UA. If there is any problem with the sensor, the OPC-UA itself gives a stats code. And now we have our data quality monitoring system monitors this stats code. Okay, so if this stats code, the OPC-UA have a lot of stats code. It's an industrial protocol. Based on this stats code, it means a type of problem in the sensor, and we monitor that. And based on that, then we can notify the local team, hey, if you are not looking, it's probably they're already looking at it, this is happening with this sensor. So we can already do that on behalf of the operation teams on site. We can already monitor them, hey, this is happening with this sensor. So the disruption itself, of course, they will not have the most recent data, but because of our monitoring system, we can already notify on site, and then they can already fix the problem. So this data will not go to the cloud, by the way, because the stats code of the OPC-UA only ingests in the cloud. When it's one of the rules of the transformation, we only send to the cloud tags. In this case, OPC-UA calls tags, the data point, that with the stats code good. So if it's not good, we're not going to send to the cloud. And our monitoring system alert the people on site, or ask the people on site, hey, what is happening with this?
And in terms of the uses of the system that you're building and the data that you're providing, what are some of the most interesting or innovative or unexpected applications of it that you've seen?
A lot, to be honest. At the beginning, I was not expecting the smart glasses, the digital twin, the analytics over alarms and events. I don't know. There is the operation set. We have one project which is we are still starting in working. It's in the early stage, where if there is an accident, we can. It's a little bit like alarms and events, but we monitor. Yeah, it's alarms and events, but we can predict or try to predict when this can happen and which situations can happen. But it's a lot of data. But I think, I don't know, from a software engineer perspective, a lot of software engineers probably they build a feature and they send it to production. They never see them using it. maybe people at Uber or Google, they see people using it. But in my case, when I go to terminals and I see people using the smart glasses now and seeing all these that dashboards, and I can see the impact, it's like, well, I was never expecting this to happen. Or for example, the energy management project, you can see it in Forbes. We talk about that, reducing the consumption of energy, for example, for me was quite mind-blowing because didn't expect such an impact like in the company itself. When we built this system, was not expecting to become like a key pillar to the company itself. It's a little bit hard to say which one it was because so many initiatives taking place because of the data that we are able to provide. Yeah, it's hard to select one. Maybe the drones. The drones inspection is nice. I was not expecting that.
In your own experience of designing and implementing and evolving this platform, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
I think when we were building at the beginning, early stage, we started very small. It was the expectations. We started with 1 or 2 sensors and people, okay, then we can already start doing machine learning. No. But at our scale, maybe the operational part of it, I was not expecting, or like example, fixing data, right? As I told you, data migration was something that we were not expecting from the beginning to be so challenging, or even giving context to the data was something we were not used to it, or expecting that to happen. So the design, while designing it, then building it, if it was now maybe the transformation lambda, so the normalization lambda. So, but this is now, right? But this can change, right? Maybe I will look at it with more careful. We focus a little bit more at the beginning in ingesting because, you need to give value. You need to give value to the business as fast as possible. And they want the data, let's ingest it. We focus a lot in ingesting the data, understanding the OPC UA protocol, how Modbus protocol works, how the industrial side of the things work. And then when it went up to the part of transformation of normalization of the data, we didn't focus so much on it, Yeah.
In terms of the near to medium term future of the work that you're doing, what are some of the things that you have planned or particular areas that you're excited to dig into?
I think the capability to run machine learning at the edge. Greengrass allows that. So they call it machine learning inference. We are doing proof of concepts with it, even in the part of the energy management. Like, for example, we see that a pump, it's consuming too much energy and we do peak shaving. You shouldn't be consuming so much energy because it's not going to be used for 2 days or 3 days because you need to warm up a pump in order to work. We send the instruction to the operator saying, hey, based on previous history and based on future schedules, this pump doesn't need to be on. And the operator can say yes or no, and we shut down the pump. So that's something that we are currently evaluating, testing to see. So the capability it's running the machine learning, the part of the AI with the help of our data team. And by the way, our data team is doing a very good and awesome work because I'm saying this, what excites us or what we're going to do next, but majority of the times is what the business wants next, and for that you need to teach. We are even creating like a data academy in-house where we teach the business, the people on site, managers and directors, what they can do with the data. And based on that, they are the ones that can give us ideas, and then, okay, yeah, we can build it and let's do it. We need the business and the people on site to help us. Without them, we are not going to solve anything.
Are there any other aspects of the systems that you have designed and implemented or the overall complexities of dealing with IoT data at a distributed scale or just the overall space of building and managing these complex data systems that we didn't discuss yet that you'd like to cover before we close out the show?
I think one thing that needs to be building these IoT systems or any distributed system or these hybrid systems is that someone wants to build it. I think first people need to think is about deployment and testing. Of course, you need to give value, but this IoT system is very hard to test, right? Because there is many factors that can change. So testing and automated testing, it's very important. Automation It's a very important topic in the IoT field. Okay. Yeah. If you control the sensors, let's say if you are a company that build your own sensors, you don't have that problem, right? But if you are someone that ingests data from different sensors, you really need that. Yeah.
All right. Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
From a technical perspective, is the fragmentation in the IoT sector, at least at the edge. Okay, it's good that companies focus in one problem, but when we were evaluating, it's very hard if you're going to need to maintain like 3 applications at the edge or 4 applications at the edge. So it's very hard to find an application that does everything and the cost is still not very high. You know what I mean? So I can have 4 applications that are not very expensive and easy to maintain and they scale, but in the long run, I will need to hire 20 engineers to maintain it. So yeah, the fragmentation. From a people perspective, is unit or management of the data is when you are deploying worldwide, as in our case, this is not a sprint. It's a marathon. You're not going to start ingesting and processing this data in one day. And everyone that you're going to deal with is going to have different expectations for it. So I think that's the biggest gap, because you're going to come as an engineer, a software engineer, full of ideas, and then the other side, you don't know what are the expectations of the people. I think the gap is a gap in acknowledgement.
All right. Well, thank you very much for taking the time today to join me and share the work that you've been doing at Vopak. It's definitely a very interesting problem space and an interesting design challenge that you've been working through. So I appreciate all of the time and energy that you have put into that and the time that you've taken to share your experiences with me and the audience. Thank you again for that. And I hope you enjoy the rest of your day.
Thank you.
Listening. Don't forget to check out our other show, podcast.init, at pythonpodcast.com to learn about the Python language, its community, and the innovative ways it is being used. And visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. If you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers.